We're waiting for one. You have the power to make this go faster if you have one. Actually, it's cable. Oh, maybe. Cool. Let's see here. What's going on? Well, now I feel bad that he's looking for an adapter that we don't need anymore. Is there any other staff from PHDays here at the moment? Are we ready to go, or should we wait? Start? Oh, hold on. Are we ready to go? Yeah? All right, good. Good afternoon, everyone. So this is a talk about an interesting topic. I call it Janitor to CISO in 360 seconds, which is about 6 minutes. And we will be discussing a very interesting attack against mechanical pin tumbler locks. So before we begin, let me talk a little bit about who I am. So I am associated with Tool. Tool is a lock-picking organization founded in the Netherlands in 2002. I am the president and co-founder of the United States division of Tool. We currently have over 21 chapters in North America, and the organization does a number of things, including public education, running lock-picking villages and workshops like the one that is here at PHDays. And principally, the organization serves a combination of both hobbyists and professionals. So we have, many competitions all over the world and meetings often concentrating only on picking locks for fun, because it is fun. Professionally, I work with a pen testing firm that I founded. We've also been around for around 10 years, and we focus on education, independent research. We do some reverse engineering work, and principally, most of our work is with red teaming or live engagements. And some risk management stuff. So we like to sometimes say that, security consultant by day, criminal consultant by night. But that's my background. So let's talk about some locks. And why are locks important? Why do they matter? Well, the reason locks matter, even in the information security world, is that if you can touch it, you own it, right? If I can physically get to your hardware, to your firewall, to your servers, we got it working. Thank you. And that's all right. Then there's a problem. And so the physical security is just as important, if not more important, than the cybersecurity. And so oftentimes all of the hard work that you put in at the data center can be undone by using the wrong locks that were purchased from a hardware store. And locks also serve another interesting function that is important to remember, which is to say that locks function as seals that are evidence of tampering. Before we had easy ways of locking up our personal belongings, sailors at sea would often use special knots in order to detect if someone has been in their bag. So if anyone in here is familiar with knots, there are some different names for them. In the US, this is something we call a reef knot, and it's a very common knot used very often on boats. And many years ago, sailors used to use something called a thief knot, which looks very similar to a reef knot, but takes a very special way to tie it. And the reason for that is at the time, thieves would look at the knot of the bag before they opened it, memorize it, look in the bag to see if there was anything interesting, and then try to tie it again with the same knot to delay the amount of time that it took before they were detected. And so the thief knot, because it looks like a reef knot, if the sailor came back and saw that, oh, it's been tied incorrectly, then they knew someone was in here. And locks serve the same function as well. The purpose of the lock is not only to prevent access, but to tell you that someone was there. If you walk into your office and the door is missing, or there's a big hole in the wall, you know there's a problem. And if there's a hole in the wall and nothing was stolen, you know there's a big problem. But if you walk in and everything is normal, and there's nothing broken, then how do you know if someone was there or not? And this is the problem with locks that can be manipulated. So today we're not going to focus on lockpicking, but in order for you to understand the exploit that we're going to talk about, you need to also understand lockpicking. So I will give you a very brief overview of how lockpicking works. The most common type of lock cylinder in the world is the pin tumbler lock. They come in a variety of shapes and sizes, and they all look very similar from the outside. Who in this room has seen this type of lock before? It should be everyone. Perfect. From the outside, they all look very much the same. And we can use some terms to define the different parts of the lock. We have the housing, or the shell. Inside that, we have the plug. This is part of the lock that turns. Inside of the plug, we have the keyway. This is the hole that you insert the key. And the keyway usually has some sort of shape. And the shape is referred to as the warding. So again, here's the outer view. And if we were to look inside the lock, this is what we would see. We would see a key pin, a driver pin, and we can see that these two work together to keep the lock closed. And normally from the outside, you can only see the key pin. So again, normally you don't see the driver pin. You only normally see the key pin. And of course, there's a spring, but this much is obvious. So without a key, does the lock turn? No. Why not? The driver pin is blocking the rotation. And it doesn't matter if the lock is installed this way or this way. They work the same way. In the US, we often install our locks like this. In Europe, often like this. I don't know what's common in Russia. Like this or like this?
Like this.
Like this? First one?
Yeah.
First one, yeah. Pretty much everywhere in the world, it's like this. But it works the same way no matter what. And of course, when you insert your key, the pin is raised to the shear line, and the lock is open. And in a real lock, there is not only one pin, there is 5 or 6, maybe 7 pins. And so when the key is inserted, each one of those key pins must be raised to the proper height in order to allow for the lock to open. And if even one pin is too low, like you see there, or too high, the lock doesn't open. It must be just right. And you can also notice that the points, the sharp parts on the key, don't matter. The only thing on the key that matters is the part that the pin rests on. And if you've never seen the inside of a lock, this is not very obvious. This is also why sometimes if the key has trouble working in a lock, if it's been copied many times, why sometimes you can wiggle it back and forth and you can make it work. Not really directly related, but interesting. In movies, we see people shooting locks a lot, so we shot some locks. And interestingly enough, even though we put holes through the locks, the shackles remain closed. And it's important to keep in mind that lock cylinders are part of a system of components. And the cylinder is not the only component of a lock. Even if the cylinder is missing, you can see the lock can still remain closed. But we're not going to talk about that today. So in a perfect world, normally when you apply any kind of pressure to the lock, all of the pins are blocking the rotation equally. But in the real world, there are manufacturing defects and problems in the lock, in the pins, that result in issues with tolerances. Does anyone see anything wrong with this lock? That's correct. It's not on a straight line. You can see that some of the pin chambers on the left-hand side are not perfectly aligned, and this causes a problem in the lock. So when you apply turning pressure, the pressure is applied unevenly, and this allows you to manipulate the lock. So again, on the left, you can see a perfect lock, which does not exist, and on the right, you see an exaggerated version of a realistic lock. And so this is how lockpicking works. When you apply pressure, you're able to raise the pin to the proper height. The plug turns a little bit, and now you can set multiple pins. And if you are interested in learning more about lockpicking, I encourage you to come to our workshops tomorrow, and you can practice this yourself. But today, we're going to talk about something different. We're going to talk about master keyed systems. And these are systems where you have large buildings or schools or institutions where there's several hundred or maybe several thousand lock cylinders. And there are some people that have keys. They only open some doors. And then there are some people that might have a master key or a top-level key that opens all of the doors. Has anyone here seen a system like this in use before, where you have one key that opens multiple? So some. It's not as popular in different parts of the world. But what's interesting is that in addition to, okay, so we're going to say this right now. If you have a cell phone, please put it on silent right now. If you have a cell phone and it's not on silent, please put it on silent. Thank you. So master keyed systems offer a couple of different advantages, and they're also vulnerable to a type of attack that we'll discuss. So how does the master key system work? Instead of only having 2 pins in a chamber, you have multiple pins. So as the key is inserted, key cuts of different heights can open the same lock. So in this example, you can see that we've replaced the number 8 pin with the number 6 pin and a number 2 pin. And what this means is that a key in that position can open the lock either with a number 6 cut or with a number 8 cut. Does this make sense? Yeah? It's a very simple concept. And using this idea, you can make very large and complicated master key systems. So you can have individual keys that open the locks, and then you can also have high-level keys that open multiple locks. So let's take a look at an example system. So here's 4 keys. We have Alice, Andy, Bob, and Janitor. And each one of their keys has a different code, a different bitting. And this is the code of the key that operates the lock. Each one of those locks is also a little bit different. So you can see here's Alice's key. Her key works in her lock in the upper left-hand corner, but it does not work in Andy's lock or in Bob's lock. Andy's key works in his lock in the upper right-hand corner, but it doesn't work in either of the other locks. Bob's key, same thing, lower left-hand corner. Bob's key works in his own door, but it will not open any other doors. Now you have the janitor's key. And you can see the janitor can open 2 of the doors, but not the 3rd door. because that's not a door that he's supposed to have access to. And about sometime in 2003, a colleague of ours, Matt Blaze, published an academic paper about using optimized attacks to decode the top-level master key. And it received, at the time, a great deal of attention from locksmiths. He even received death threats for publishing this very simple paper. And it was news for a couple years, and then it was quickly forgotten. And what's interesting to us is even today, 13 years later, we still see the same problem in all sorts of systems all over the world. And what's interesting about this attack is if you compare the cylinder parts to how cryptography works, you can think of the cylinder as an oracle. Think about, what does the oracle check? What does the cylinder check when you insert the key? It checks the key bidding. And how does the cylinder respond to the key? It either opens or it doesn't open. So it gives you feedback. Is the key correct or is the key incorrect? Now, using what we know about locks, how can we extract information from the oracle? How can we get the oracle to leak secrets to us? Well, let's take a look at that. So here is Alice's key. This is a lock that she can access. This is her own door. So her bidding is 36235. Obviously, it works in her lock. We don't know what's inside the lock, but we know for sure, at the very least, all of the driver pins must be at the edge of the plug. So at the very least, we know that this is correct. But if the system is master keyed, we also know that there are other pins in the lock. We just don't know where. These details are hidden to us because we cannot see inside the lock. So what do? Well, we can attack the lock pin by pin because the pins don't talk to each other. So what we will do is we'll first take some blanks and we're going to copy Alice's key. Except in the first position, we're going to leave it 0, uncut. And on all of the other positions, we're going to use the cuts that we already know from her key. What we're going to do is we're going to sweep through this range. We're going to only concentrate on one bit position at a time and move through it and check it each time. So here's the first key. We file it away. We put it in the oracle. And the oracle says, no, the key does not open. So we know that the one position is incorrect. And we keep going. We try the number 2. If you're filing by hand, your cuts might look different. But remember, the only thing that matters is the lowest point where it touches the key. So we try the key again. The lock doesn't open. So we try it again. We go down to 3. So what's going to happen? Is it going to open? Yes. Why? It's the same key, exactly. We already knew that this was the correct bidding, the correct bidding, sorry, and we've now duplicated that. However, we've learned something. We've learned that at the very least, this pin is solid. There might be more pins above it, but we know for sure that this pin is solid. So we have to continue exploring. So we file down one more position, we try the key, and find that it doesn't work. We keep going, try number 5, try it again, doesn't work. Keep going, remove the key, file it down to number 6, try it in the lock, open. Now what have we learned in this example lock? We have learned that there is another pin, and we have learned the height of that pin. So without opening up the lock, we've discovered this other pin height. Now we know this one. And we can repeat the same process for the rest of the pins. There is a chance that there are more shear lines. So if we want, we can continue exploring to number 7 and try it. But in this case, in this example, it did not work. So we know in the first position, there was only a 3 and a 6. And you can do this for any position. Now, in this example lock, we're using a Kwikset brand lock. It's an American lock that you'll never see here, thankfully. It's terrible. There are only 7 positions per chamber. So we don't not have to go past 7. So now we're going to prepare a second key. And we use the 6th position in the first part of the key, because that's what we've already learned. In the second position, we put in a 0. And the rest we put in from the original key. 0 depths with no cut are very rare. They're not used very often. So if you're trying to save time, you don't have to check 0. But it also doesn't cost you a lot of time to check 0. So in this example, we'll start at the number 1 depth. We try it. Lock doesn't open. File it down to number 2. We try it on the lock. Still doesn't open. And we keep going. We're at 3. Try it again. Lock doesn't open. Keep going. Try the key. Open. What have we learned now about this position? Well, we know the number that we learned is different from our original key. So we've now discovered the other master pin in this chamber. Now again, we don't know about these, but we probably have all of the information from there, because now we have a shear line here and a shear line below it. Because we know all the other positions from our original key. So now we're basically done with position 2. Why? In practice, single pins are very rare. They cause problems in the lock if the pin is too thin. So you can usually, in most systems, if you're performing this attack, you can skip numbers. You don't have to try each consecutive number once you reach a successful position. So because of that reason, a 5 depth is unlikely. So we could try a number 6, and that would work. But we know that because we knew that from before. What about 7? Should we try number 7? No. Why? Because then yeah, exactly. We wouldn't want to try number 7 because it would be a single position pin, and this would be very rare in the lock. So, and since quickset locks in this example don't go past number 7, we don't have to keep going. So now we prepare a third key. Which cut will be in the first position? 6, yep. Second position? 4. Third position? 0. We have some people listening. And for the rest of the key, do you remember? You may not. It's okay. 3 and 5. Very good. So now we explore this position. And as you can see, through this process, it's very, very simple. This is not complicated. And this is also something that you can do without arousing any suspicion. Because you're not picking the lock. You're not using any tools. All you're doing is you're inserting a key into the lock and seeing if it opens. Someone watching you even on a camera will only see you inserting the lock and trying to open it. And you can pretend that you were at the wrong door. Or maybe you have access to that door. Maybe it's your office. You can do this on your own door without touching any other doors and discover information about the rest of the system. So, should we try number 1 or 3? Well, no, because we know that our original key was 2, and we know that single positions are very rare, so we can optimize our attack, and we can jump right to number 4. So, our third key is prepared. We try it. It doesn't turn. We keep going. We try it again. And open. So what does that tell us? Well, it tells us quite a bit. Now we've learned even more information about the lock. We don't have any news yet about the final 2 positions, but otherwise we think we probably have the third position. Do we need to explore number 6 or number 7? No? Why? 7 maybe, sure. If you're not sure, you can check. But if you know that there's going to be only one position, if it's not a very large system, you don't really have to keep going once you've discovered already one of the depths. So now we prepare a 4th key, 6, 4, 5. We put in 0 for our cut. put in 5 for the last cut because we already know that from before. And why are we skipping 0, 1, and 2 and going directly to 3? Well, we're actually not, sorry, I apologize. You caught me. We're going to test 1. We know 3 was our original height, so we're only going to test 1, then we're going to test 5, 6, and 7. So we go to 1, we try it, doesn't work. We go to 3, we know that that works because that's our key from before, obviously. So we try 5, doesn't work. We try 6, still doesn't work. And we try the last one, and it still doesn't work. What does that tell us? There's no master pins in that position. So position 4 is not mastered. Now we've decoded 4 out of the 5 pins. And so now we prepare our very last key. So now the 5th position is free to be explored. We could try 0 or 1. So we'll try number 1. And it works. So what have we probably discovered at this point? There's a very strong chance that we've probably discovered the master key for that system. What's the easiest way to check if that key works? Just start trying it indoors. Yeah. Walk around to different doors, try it, and see if it works. That is all you need to do to decode a master key system. It's possible that there could be another cut here, and maybe there's some other cuts here. But if you just start trying it in different doors, then that could be all that's necessary in order for it to work. Now, if you've done it with a machine, your key will look something like this. If you've done it by hand, your key might look something like this. If you've done it by hand poorly, it might look something like this. It might get stuck in the lock. So be careful you don't do that. But let's take a look at our original locks again. So here's our original lock, and you can see the master pin depths as well. Here is an alternate lock in the same system. A new lock, a different lock. That's part of the same master key system. Our decoded master key would work there as well. And this is an attack that took you what, 20 minutes to learn? How much time do you think it will take to work through all these keys if you have them prepared in advance? At most. If you want to do all the cutting, and you're counting the amount of time that it takes to cut, sure. But what's interesting about this is you can prepare all of your attack keys in advance. If you have your working key already that you're going to use, you don't have to go back to your key machine between each test. You already know all of the possible keys that you're going to use. And key blanks are very cheap. They cost, in 10, 20 US cents. So you can buy 20, 30 keys, however many you need, and prepare all of your exploratory keys in advance. And you can go through all of these keys very, very quickly. Now, with this attack, is there any evidence left in the lock? Yeah. No. Normally, with lockpicking, there's forensic evidence left in the lock, scratches here and there. With other techniques, there's always forensic evidence left behind. With this particular technique, there is no forensic evidence left behind because all you are inserting into the lock is a key. If you perform this attack, do you think it's easy to detect? For others, no. So what do you do? If you have a master keyed system, well, you could just not use master keying, but master keying provides a level of convenience that a lot of customers enjoy. If you have to use master keying, I would maybe recommend that you take your important assets, such as server rooms, wiring closets, laboratories, and don't make it part of the master key system. There's no reason that every door has to be master keyed. It's okay for whoever is important enough to have access to everything. It is okay for them to carry 1 extra key, 2 extra keys. Or alternately, you can use systems from different companies that combine mechanical elements with electronic elements, such as, the ASA click. This is a lock cylinder that uses a combination of a cryptographic electronic token in addition to high security mechanical elements. That's basically it. This is something that, even though it's a very simple attack, and even though it's an older attack, we have run time and time again into clients that have never heard of this. Had anyone heard of this attack before today? No. Is it kind of a scary attack if you have a master keyed system? Yeah, sure, absolutely. So that's the basic idea. We have some time for Q&A. I have a lot more content. If anyone has any specific questions about a topic, I think we have a good amount of extra time, so I'd be happy to switch to that as well. And that's what I have about master keying. So thank you for that. Does anyone have any questions? Yes, in the back. So we have microphone moving to the back. And we have a question here.
If I understand correctly, you are taking a usual regular key and you're trying on your own office.
Correct.
And you try each pin one after the other. But this assumes that the master key is totally opposite from the regular key. And what happens if the master key is part of regular key and part of extra pin you guess at this time? I don't know if I'm clear.
Ask me the question once more. I'm very sorry.
Okay. To perform this attack, you take a key, your regular key, you put it in the pin, and one after the other, you are guessing the missing part.
But you're checking it, yes, yeah, that's correct. One by one, that's correct.
One by one, but and then you eventually find every part who doesn't belong to the original key.
Correct.
So you assume that the master key is only constituted by the opposite part you just find.
Correct.
And if it's only a combination of your key and the extra pins you found, so there are a lot of possibilities.
Yes, I understand now. So what you were saying is that in this example, we're assuming that any pin depth that we find that is not part of our original key is part of the master key.
Yeah.
If the system is a smaller master key system, then this will almost always be true. If it is a system that uses multiple keys, so if it looks closer to, let's see here, one moment. So for example, if you have multiple levels.
Yes, intermediate ones.
If you have intermediate levels, yes, then you will discover possibly multiple master key depths. And then you will have a situation where you might accidentally discover one of the intermediate keys. And you will have to do some more testing and more exploring to figure out the actual master key. So what would happen is if I am in this system, I'm guessing which cuts are the master pins. So what will happen is I will start trying it on doors, and it'll work on maybe 5 or 6 doors, and then it won't work on another door. And then I know, or I can assume perhaps, that one of my pin positions maybe is not correct. So then I can again use that door as another test case, and I can test the other heights. So with larger and more complicated systems, there is certainly a little bit of more work that is necessary. But you're still deriving a lot of very important information from the lock without doing anything invasive and without doing anything complicated. It's very much like if on a computer there was something that you could do where it would tell you what characters were in the password. It reduces your key space considerably, and it makes the brute force attack very, very fast. Does that help answer your question?
Yeah, just if there is only two possibilities, of course it's very easy to know for sure that your key is master key without spending time to office where you don't are supposed to be. So then
Right.
you have to check, even if you are checking a small amount of possibilities.
Yes, if it's a small system, you can assume that the other height is the master key. But if it's a large one, you will have some more work. Yeah, sure.
Thank you.
There was a question here. Yes.
Hello. My question is, do you think that it is possible to build some device that will do it automatically without, cutting manually?
That's an interesting.
There is some kind of
That's an interesting
proof of concept or something like that?
That's an interesting question. So actually, it should be possible. I'm going to try to find a picture of a tool here. While I'm looking for this, there's no HDMI here, so I can't connect my phone. And I'm not going to connect my computer to Wi-Fi. Okay, so I'll just have to explain it. I apologize. I was going to look it up online. If you search Google Images for the Sputnik lockpick, it's a device that has a key with holes in it, and it has wires coming out of the holes. And the purpose of this is to be able to change the heights of the pins without having to use different keys. And it's a very advanced lockpicking tool. And if you, in theory, were to connect such a device to, say, some motors or some servos and use some different sensors, then yes, it should be possible to build a brute forcing tool. It's quite possible. It would be some work, and it wouldn't be cheap, but it would be very possible to make a brute forcing tool. I would say so. Sorry? Was the question, do 3D printed keys work? Yes, 3D printed keys absolutely work. There's been, that's a great question. People have done a lot of testing with 3D printed keys, and they don't have to be very strong in order to work in the lock. In fact, there are programs that you can download that will automatically generate the STL files that you need to 3D print keys. So you feed it a code, you feed the program a code for the key, and it'll automatically create the STL file that you send to your 3D printer. So if you wanted to make the attack more simple, more automated, and you don't have access to a key cutting machine, then in theory you could write a script or a small program that creates these 3D models for you automatically, and you could say, type in the code for your existing key, and it would automatically print a bunch of keys for you to try. And this way you don't have to file anything, you don't have to cut anything on a key machine. Almost anyone with a 3D printer would be able to execute the same attack. That's a very good question. I actually hadn't thought of that until you asked it. Thank you. Here and then here, yes. Can we give him a microphone? I'm sorry, I'm having some trouble hearing you. One moment. Perfect. Once more, please.
You say this attack very hard to detect for forensic specialists.
Yes, correct.
But what if we say about security service? They can see each camera that some person stay in front of door and try to open door with many keys.
So that's a very good question. I'm glad you asked it. So if you're saying if there is a camera and there's someone at the door with, 20, 30 keys, that looks a little strange, and I would agree. You have to remember that this is not an attack you have to do all at once. When you think about lock picking, if you stop picking the lock partway through and you let go, everything is reset. You have to start from the beginning. So sometimes it is necessary with traditional lock picking to be in front of the lock for 10, 15, 20 minutes. And this is very easy to detect. However, with this, you can spread the time of your attack out over the course of days, weeks, or even months. So if I am a vendor, let's say I I change the air filters in a server room or something. I'm an outside party, and I only go there once a month. That means once a month, I can try 1 or 2 keys. And if you're fast enough, it can look like a very normal thing, especially if you pretend that, you're on your cell phone, you're talking, you walk by the door, and you try your key, and you're like, oh, it's not the right door, and then you keep walking. And so if you combine this with social engineering, and you're a little bit smart about how you test your keys, then it becomes, again, much harder to detect. Impossible? No, but very, very difficult. Does that sound more reasonable? Instead of doing all the keys at once?
Yes, thanks.
And we had a question here too, so okay, we'll go to you.
How often you see master key systems in your practice?
Once more, please.
How often master key systems exist in the world?
How many master key systems are there in the world?
How many? How often?
That's a good question. I don't think there's any official numbers. I think it varies depending on the part of the world, in my opinion. In North America, master key systems are extremely, extremely popular. I have found that in much of Eastern Europe and in Asia, they're not as popular. And the reason for that is because of the diversity within the locks and because people seem to change their locks more often. And so master key systems aren't as practical. There also aren't necessarily as many institutions that are interested in spending the money and the labor of paying a locksmith to master key a system. If you consider the extra work that goes into repinning each lock from the factory, and you multiply that by the number of cylinders that you have, then some customers may not be interested in paying for that. It might be cheaper just to have a bunch of different keys. And this is why, some people have a key ring with, 100 keys or something on it. I can't say how popular it is here because I don't spend a lot of time in Russia, unfortunately. But I can tell you, at least in the US, master key systems are very, very common. They're very popular. Every university that I have been to has had a master key system. Every major office building that we've visited has had a master key system of some kind. And you won't find it in smaller businesses, but if you have any businesses that have hundreds or thousands of doors, then there is a higher chance that they might have a master key system. Does that answer your question?
Yeah, thank you.
And I think we have a question here.
Are there any mechanical means of protection against this type of attack if we need to use master key?
Are there, the question was, are there any protections or mitigations against this attack?
Mechanical protection.
Mechanical protections. Unfortunately, we're not exploiting a defect in the lock. The lock is working exactly as intended. And any kind of protection that we come up with would break the master key system from working. So this attack is more a problem with the entire idea of master keying and less a problem with the individual design of the lock. So really the only practical way to deal with this attack is either to not use master keying or to use different locks for doors that are very important, or just to use a electromechanical system that combines, as I mentioned, something electronic with something mechanical in the lock itself. Not access control, not RFID, but something electronic in the key as well. That's unfortunately, none of those answers are very good. So the short answer is that there's no easy way to avoid this and still have master keying.
Thanks so much.
Here's the question.
Okay. Any more questions?
Yes, I
Yes.
have one.
Oh, yes.
Is there any way to create the first key? In this attack, you show that I have one key that opens at least one door. And I assume, as I know the lock system, but I don't have any key.
Okay. So the question is, right now we are starting with some information.
Yes. How to craft the...
If we have no information, what do we do? You have a couple of options. One of them is you could pick the lock with something like the Sputnik tool that I described, which uses, wires, and then decode it that way. The other option is to use a technique called impressioning. And actually, I can show it briefly since we have some extra time. If you guys are interested. Does anyone want to see another covert lock opening technique? So with impressioning is another technique that often is used by intelligence agencies and locksmiths alike. And we'll do this. Here we go. So with impressioning, we can take a blank key and turn it into a working key to get exactly the type of information that we're looking for. And with impressioning, when we insert a blank key into the lock, and I apologize to the translators, they don't have a copy of this slide deck, so they're trying their best right now. You raise the key to the maximum height, and if you turn the key really hard, like with some pliers or something to hold the key with, then some of the pins in the lock get stuck, they bind. And as you move them up and down, they create a small mark on the key. The mark tells us that this pin is not in the correct position. And so by removing the material and performing this over and over, we keep going. And anytime we see a mark on the key, we remove the material and we try again. And what happens when the key pin reaches the proper height, then there will be no mark because that pin will not be getting stuck. It will not be binding. Instead, there will be a mark that appears, a new mark that appears. And these marks are, just so you understand, they're very, very hard to see if you're not trained. Does anyone see a mark on this key? It's right there. It's that little dark spot. It's very delicate work. It's something that requires a great deal of practice, far more practice than lockpicking. But you can very quickly create working keys for a lock. I think we might even have, here is, let's see if this video plays. It does not. Oh, sorry. We had a video and it doesn't work. But this man here, this is Jos Vyas. He is currently the Dutch impressioning champion in our games, our global championships. And he is able to impression open a Abus 6-pin cylinder in about 1 minute, 20 seconds by hand. So if you use such a technique to create a working operating key, then you can then combine it with the master key attack and decode the master key. So that would be one example that I would use. Yeah, and now we're out of time. Yeah? Okay. Thank you very much, everyone.
Choose your favorite questions to get them your small presents.
Shoot.
Microphone.
I don't know. I don't know.
Just think about that.
Друзья, еще
I liked-
футболочки за вопросы.
I liked the 3D printing question because that was a good idea.
Окей. Девушка, вопрос про 3D принтер, который вам футболка. Футболка? And the next one?
The last one. His question was a very good one. Yeah.
Thank you very much.
Thank you.